All right, today we're going to get into chapter 12, which is solutions. Primarily, it's going to be a vocabulary session. So these are terms that I expect you to remember, and we're going to get primarily into more molarity and molality during class. As you can see, wearing my mountain biking outfit, so just coming fresh off a little ride from the snow. I don't know if you noticed, but this afternoon it snowed. So just go through some of this stuff real quick. A solution. This whole chapter is about solutions. It's a homogeneous mixture in a single phase. So the key is that you take some solid sugar and some water. You dissolve the sugar into the water. It looks like just water. So the water ends up being in the liquid phase. Homogeneous means same throughout. So vocabulary soluble means that it can be dissolved. If you throw the solid into a liquid and it just goes to the bottom, doesn't do anything, then that is not soluble. Solute, that's the compound that is dissolved. Solvent is the compound that does the dissolving. Sugar would be the solute. Water is the solvent. All right, well, get ready to pause because we're moving. Let's see here. I'll just go at this angle a little bit. Don't need that. I think that gets... Yeah, we'll just go at a slight angle here. I know some of the writing's a little light. Basically, we can go through experiment and see if something's going to be soluble or insoluble. Another way to describe it kind of in physical property sense is by particle size. So we have a suspension. That's the idea of like a salad dressing that's in the jar or the container, the little bottle on the grocery store shelf. If it's the one that's been sitting there for a while, you can see the different layers. Well, if you shake it up, you'll form a suspension and it will separate over time. And this particle size is in reference to solids. It's not in reference to two liquids like oil and water. We're going to talk about that in a second. These particle sizes are in reference to solids being in the mixture with a liquid. A colloid, that is a heterogeneous mixture, like a suspension is a heterogeneous mixture. It's a mixture that will not separate. And those are typically 1 to 1,000 nanometers. A suspension greater than 1,000 nanometers. A colloid will not separate, but it's still not a solution. A solution is the same throughout. Emulsion is a special kind of colloid. That's two liquids that won't separate. For those that enjoy cooking, if you are, there's so many recipes. Like if you're making your own salad dressing from scratch, you're going to take vinegar and oil, and you're going to slowly drizzle in the oil with whisking. That is making an emulsion. If you're able to get the oil and the water parts so small, they won't come back together and separate. That's a really good emulsion. That's two liquids that won't separate. Mayonnaise is an emulsion. If you've ever seen homemade mayonnaise, that is an example of an emulsion that will not separate. A solution then is where the particle size is less than 1 nanometer. Real quick, electrolyte, non-electrolyte. This is all that it really comes down to. Is an electrolyte is a solute that will make a solution that can conduct electricity. Basically, that's going to be your ionic compounds, salts, acids, bases, those things that make charged species when it goes into solution. A non-electrolyte is a solute that makes a solution that cannot conduct electricity. Those are going to be your molecular compounds like sugar. A sugar solution versus a table salt solution. A table salt solution is an electrolyte. Salt is the electrolyte. That is a solution that can conduct electricity. Sugar dissolved in water is an example of a non-electrolyte because sugar is a molecule that doesn't have a charge when it's dissolved. It stays as the sugar molecule. All right, you got that? All right. Rate of dissolution. Dissolving. What is the dissolving process? The dissolving process is like an example of water. We have this solid here that has multiple parts to it. So imagine these little squares as being parts of an ionic compound. A water molecule will come and attach, well, it may not attach, but make a bond with one of the ions of the ionic compound. What ends up happening is the water binds tighter with that ion than the ionic compound does itself, so it ends up pulling the ion away. And that's what ends up happening one at a time. The question would be, would this one be able to get dissolved? This one that's inside, not directly exposed to water? No, because dissolving can only occur on the surface. So we got to remove these outer ones first. Now, how can we change the rate of dissolution? 3 ways. Increase surface area. Well, an example of that would be you take, I want to use the example of sugar. I don't know, like rock salt. So you get like really big chunks of rock salt that go into a salt grinder. So you're like, get the freshest salt. Well, if you took those rock salt chunks and then found a mass, and then took the rock chunk salts, an equal mass, ground them up, same mass as the big chunk rock salt, put them both in a glass of water, and waited to see which one was going to dissolve first, the ground one would dissolve first because there's more surface area, more possible interactions with water molecules. The second would be to stir. You make your delicious sweetened Lipton iced tea with the dry mix. Put it in, down at the bottom, it all gets like deliciously tan and iced tea-y at the bottom. Well, at the top, you still have this clear water. Well, that's not as delicious as the sweetened tea. What do? You stir it. What that does is it brings fresh solvent. Because we're going to get into saturated and unsaturated in a second. And we'll connect that to this idea. But we stir it to bring fresh solvent. Heat. Well, we can add heat. Heat has 2 effects. Heat will increase convection, and convection is that moving of densities. So you heat it, the particles spread out, they get less dense, which means they go up. And then to replace that is the colder, closer, more dense liquid goes down to the bottom, it gets heated, it expands, it goes up, cools, contracts, becomes more dense, goes down. So that's the kind of idea of stirring. Also, a heated liquid typically can dissolve more solid than an unheated. So those are the 2 ways that heat can have an effect. All right, I'm going to try to make this less than, well, it's probably not going to happen. This is going to be probably just a little over 10 minutes. You don't like it? Too bad. We're just going to do this part here. Unsaturated, saturated. Unsaturated is, I'm just trying to see if we can see it because of the glare. All right, I hope you can read it. Unsaturated. That means that it's under the amount of solute at that temperature. We're going to talk about temperature and solubility in a second, so that's where we're going to be going next. But saturated, unsaturated. Saturated means that it has the maximum amount of solute for that temperature. So we can make a saturated solution, heat it, and then it becomes an unsaturated solution because at a higher temperature, liquids can typically dissolve more solid. And if we have a saturated solution and then lower the temperature, we can create a supersaturated solution. Supersaturated solutions are solutions that hold over the amount of solute for that temperature. Solvent, just to kind of talk about the different solvents. Water is a polar solvent because water is a polar molecule. We also have non-polar solvents like, non-polar solvents. Crap. I was trying to think of some stuff from organic chemistry. I'll see. See, I just don't want to lie to you. Tetrachloromethane? No, I don't think that DCE? Dichloroethane? Maybe dichloroethane. We'll figure that out. A polar solvent can dissolve polar compounds. A nonpolar solvent can dissolve nonpolar compounds. And what it comes down to is the common statement, likes dissolve likes. Moving the desk. Moving the desk. Next section, Henry's Law. Ooh, a little bit closer. Henry's Law relates pressure and the amount of gas that can dissolve in a liquid. Pressure of a gas can above a liquid, so it's in a container. Think like a soda bottle, right? So a soda bottle freshly off the shelf, you squeeze it, it's really hard to squeeze. It's like a rock. What that is soda manufacturers, they want maximum carbonation for you when you go home and you can drink it and you're like, oh, it burns my throat and stuff. Well, that's carbon dioxide coming out of solution. When you crack it open, you hear the carbon dioxide rush out. If you crack it open really quick, you'll see bubbles actually come out of the soda in the bottle. That is because now that you've broken the seal, atmospheric pressure is now the pressure of the system because it's exposed. Well, Henry's Law is you've lowered the pressure, now the amount of gas that can dissolve is going to go down. Which means that it's a supersaturated solution of a gas, and it's going to want to undo that so the gas comes out. Temperature and solubility. How does temperature affect solubility? Most solids dissolved in liquids, you're going to be able to dissolve more. So generally it increases. But just like chemistry and every other rule, there's always an exception. Always an exception. For gases, though, it's the opposite. Gases in a liquid generally decrease. Now the question is, what is it about the particle motion between a solid and a gas, a liquid trying to dissolve a solid and a liquid trying to dissolve a gas that would cause an increase versus a decrease? We're going to talk about that in class. One last thing. We're almost there. Under 15, guaranteed. I just want to talk about enthalpy of solution. That is the heat associated with dissolving. And this is something that maybe we'll be able to do in class. So 25 minutes, I'm not sure if it's going to be long enough to wrap up this discussion. But we can experience this. We have enthalpy, your capital H, fancy for heat. So we have a change in enthalpy for the solution. If the enthalpy is positive, greater than 0, that is this situation. Heat is going into the system. We're adding heat to dissolve and make the ions. So we have our ionic compound. We're adding some heat. Water is the solvent. We put solvents above the arrow. This is one where the change in enthalpy would be positive. If your delta H, your change in enthalpy for the solution is less than 0, then that means that heat is leaving the system. You're creating, what feels like us is creating heat, right? Because heat is leaving the chemical. Heat is going out of the system, and that's when we feel it hot. This would feel cold. This is your ice pack. So if you ever experienced an ice pack, you shake it, there's some water and some solid, you pop it, the solid dissolves in the water, holy crap, all of a sudden it's cold. It feels so good on my wound. That's this. Sodium hydroxide is the opposite. When sodium hydroxide dissolves in water to make the ions, heat is produced, making delta H positive. Oh, that's it. Check out the assessment now. Thanks for being patient enough with the 15 minutes. But check out this hat with the nice shirt. It looks good, right?